Welcome back. Let's look at the polar transformation t, which is given by x equal to r cosine theta and y is equal to r sine theta. So if we have, let's say we have this double integral of f of xy over the plane region R, and we want to, so let's say we change the variables from xy to r theta via t, then the new integrand will have two factors, where the first factor is obtained by substituting x and y by r cosine theta and r sine theta in the original integrand f. And then there will be a second factor, which we know is the Jacobian of this transformation t, and then d, the new region of integration, would be the inverse of t applied to the original region of integration. Now the Jacobian here is r. That is, actually, this is the absolute value of the Jacobian here is r, and the Jacobian here is the 2 by 2 determinant, where the entries in the first row are partials of x and y with respect to, the entries in the first row are partials of x with respect to r and theta, and the entries in the second row are partials of y with respect to r and theta. So if we compute the partials here, we get this, and we see that the determinant is r cosine squared of theta plus r sine squared of theta, and if we factor out r, we get r times cosine squared of theta plus sine squared of theta. And since this sum here is 1, we get that the Jacobian is equal to r. So when we make this, when we are looking at this polar transformation here, we're going to assume that r is positive, or rather non-negative, and so the absolute value of the Jacobian is also going to be r. Okay, so let's say that we are looking at, so let's see now a couple of examples of how this polar transformation work. So let's say that I have this green straight line in the r theta plane, where, so here this is a line where, given by the equation, theta is equal to pi over 6. So in the r theta plane, this is drawn. This equation is thought of as a rectangular equation. So as a rectangular equation, the graph of that is this straight line here, and I'm taking r non-negative here. So this line here would be, this horizontal line in the r theta plane will be mapped onto this ray in the xy plane, where the ray makes an angle pi over 6 with the positive x-axis. And to see this, notice that if I pick a point on this horizontal line, then the second coordinate of the point would be pi over 6, and this first coordinate would be some value r. And so x would be r cosine pi over 6, y would be r sine pi over 6. So x is r cosine pi over 6, y is r sine pi over 6. And then if we look at this right triangle, we see that this hypotenuse would be equal to this number r. And this is by the Pythagoras, or if you know from trigonometry. Now so recall that this ray here is the graph of this equation. If I think of this as a polar equation, so thinking of this as an equation in polar coordinates, then the graph of that equation in the xy plane is this ray. So the polar transformation here maps this horizontal line here to this ray. Now, if we look at this vertical line, r is equal to half in the r theta plane, again, thinking of them as thinking of this equation as a rectangular equation, then the transformation T maps that onto a circle of radius half. Why is that the case? If I take a point half, if I take a point on this line, then the first coordinate would be half, the second coordinate would be some value of theta. So then x would be half cosine theta, y would be half sine theta. So x would be half cosine theta, y would be half sine theta. So then we know that that's exactly going to give us a point on the circle of radius half from trigonometry again. So notice that the if we take theta from 0 to 2 pi, then we get this circle exactly once. So, but if we take the entire straight line here, then this is not a one-to-one mapping. But if we take theta from 0 to 2 pi, then we are getting a one-to-one mapping here. Okay, so now another example here. So let's say I have this region D in the r theta plane, where it's a rectangular region, where it is bounded by the sides. R is equal to half, R is equal to 1, theta is 0 here, theta is pi on this side. And T maps the red segment to the red segment here. It maps the blue segment to the blue segment here. It maps the green side to the circle of radius, upper half of the circle of radius 1. It maps the purple side to the upper half of the circle of radius half. Again, that's something that we know from the previous example. And then the other two sides, so here theta is 0, so that's going to go to this segment. Here theta is pi. So in terms of polar coordinates in the xy plane, when theta is pi, that's where we get the polar axis is on the negative x-axis. The polar axis is directing toward the negative x-axis, and we get this segment here. Okay, so the point is this transformation takes D into this the rectangular region D into this annular region R in the xy plane. Okay, so and one more example here. So if I have the graph of the equation R is equal to sine theta in the r theta plane, so I'm thinking of this as a rectangular equation, and this is the graph of that rectangular equation. Then T maps that into a circle of radius half, centered at the point 0 half on the y-axis in the xy plane. So basically the T maps this curve here onto the graph of this equation in the xy plane as a polar equation. So here we are drawing this equation as a polar equation in the xy plane, but here it is drawn as a rectangular equation. Okay, so T maps this curve into this curve right here. So generally, let's say we have this region D in the r theta plane, where D is bounded by a theta equal to alpha here and theta equal to beta here, and R is equal to h2 of theta and R equal to h1 of theta. Again, when we are drawing this, when we are drawing h1, h2, we are drawing them as rectangular equations in the r theta plane. Now T maps that D into or onto this region R, and this is a polar region where it is bounded by the ray theta equal to alpha, the ray theta equal to beta, and the graphs of these two equations, and we are thinking of them as polar equations. So they are drawn as polar equations in the xy plane. And so if we integrate, if we are integrating f of xy over r, and we are making this polar substitution. That is, if we replace x by our cosine theta, y by our sine theta, then we have this extra factor, which is the Jacobian, or the absolute value of the Jacobian, and then the new region of integration under this substitution is D, where D is this plane region in the r theta plane, and D is a type 2 region, if you recall from the previous section. And over D, the double integral over D can be written as an iterated integral. So integral from alpha to beta, integral from h1 to h2 of these integrand right here. So the double integral over D here can be expressed as an iterated integral because this is a horizontally simple region. Okay, so this is it. In the next video, we will continue with this polar substitution. See you then.